Okay, welcome to electrical machine lecture. In the previous lecture, we have classified the DC generator, and based on their classification, we have carried out 2 or 3 numericals based on EMF induced or the calculation of EMF and armature current. Now today, we will see the electromechanical energy conversion principle. In the very first lecture, we found that the DC generator or the EMF induced in the DC generator is based on the Faraday's law of electromagnetic induction. The Faraday's law of electromagnetic induction has 2 parts. One is the statically EMF induced and second is the dynamically EMF induced. Statically EMF induced, it means that the flux produced by the coil is also stationary, and the EMF induced, the second coil which induces the EMF, also both are stationary. Whereas in the dynamically EMF induced, the fluxes are constant, whereas the conductor is moving under the influence of magnetic flux, or vice versa. Under such condition, the EMF generated by the conductor or EMF generated is always alternating, and which is make a unidirectional in the external circuit with the help of commutator segment. All these things we have considered. Now the EMF induced, direction of EMF induced is found by Fleming right hand rule. Whereas for the motor, the mechanical torque or mechanical force is going to determine with the help of Fleming left hand rule. So now today we will see what is the electromechanical energy conversion principle. The energy storing capacity of magnetic field is much more greater than the electric field. So whatever the electric field produce, and if we are using the electromagnet, the meaning is that we are using some magnetic material, and over which magnetic material we are carried out some windings or turns over the magnetic material, and this coil or this conductor is energized from the some electric field. So it produces a magnetic field. So this magnetic field is much more stronger than the electric field produced by the current carrying conductor. In view of this, the electromechanical energy conversion devices, it may be a motor and it may be a generator, with magnetic field as a coupling media between electrical and mechanical system is more common in the electrical applications. So what is that? In an energy conversion device, output of total energy is equal to the sum of energy is converted into the required form, and some energy is stored and the rest of the energy is dissipated. What it means? Suppose we are considering a system whose input is electrical energy. So here the input is electrical energy, total electrical energy input, which is equal to the mechanical energy, that is the required, that is our required energy, or we want to convert electrical energy into the mechanical energy. But the conversion is not only from electrical to mechanical, but some of the energy is going to stored in the magnetic and rotating part, whereas some of the energy is going to dissipate in the form of heat, and it is due to the losses. This is due to the losses. Losses in electrical system, losses in the mechanical system. Losses in electrical system is the I square R loss, that is when the current flows through the conductor, it produces heat, depend upon the amount of current and resistance of material. One more thing, when we are using the magnetic material, it has 2 types of losses. One is called as a hysteresis loss, which is depend upon the type of material, and second is the eddy current loss. So to avoid the eddy current loss, we will make the core is a laminated, which we have discussed. And in future also, we are going to discuss in detail what are the different losses in the machine. So shortly, the total electrical energy is converted into the mechanical energy. Some total energy is going to stored, some energy is going to stored, and some energy is going to dissipate. So this equation 1 is for the motor because we are converting electrical energy into the mechanical energy. So this is equation for the motor. Vice versa, we can write as a generator. For the generator, we can write as total mechanical energy because we want to convert mechanical energy into the electrical energy with the help of generator. So mechanical energy is equal to the electrical energy plus total energy stored plus total energy dissipated in the form of heat, where the total energy, total electrical energy input from the supply main is say WEI, input electrical energy. Total mechanical energy or output of the mechanical energy is WM0. M stand for the mechanical and O stand for the output. Therefore, the total energy stored in any device, if you are considering a generator or motor, so which is equal to the energy dissipated in the form of in the electrical system, that is called as a resistive loss or ohmic loss, plus energy dissipated in the core. So it is due to the magnetic material. This is stand for the hysteresis loss, which is depend upon the material. You have already learned the hysteresis loop. And second is the eddy current loss, plus energy dissipated in the mechanical system. It is called as a windage and frictional loss. So there is some windage because we are using fans on the shaft of motor for the cooling. So it also provides some resistance, some also provides some losses, and the friction which is going to happen in the bearing brushes over the commutator segments. So energy balance equation can be written as WEI is the electrical energy input plus mechanical output plus energy stored. This is the energy stored, and ohmic energy loss. So this is the loss component. This is the stored energy. Stored energy. This is the losses or losses in the form of heat. So ohmic loss, ohmic energy loss, coupling field loss, and mechanical losses. Now we can rewrite this equation by bringing the electrical energy one side. So WEI minus ohmic energy loss. This is the ohmic energy loss, that is nothing but the I square R loss. So it is I square R loss is there. So under such condition, which is equal to mechanical energy plus mechanical losses, mechanical loss and mechanical energy storage plus some coupling losses, isn't it? So therefore, the W electrical energy is equal to the mechanical energy plus stored field coupling or stored energy loss or field coupling is there. So now where WE electrical is the net electrical energy input, including the ohmic loss. W mechanical is the total energy converted into the mechanical form, means gross mechanical energy conversion. The gross mechanical energy conversion is the sum of useful energy which is going to use on the shaft of the motor or shaft of the generator. So sum of useful mechanical energy plus mechanical energy stored and mechanical losses. So it is the net mechanical power converted from the electrical input. Whatever the you are giving electrical input, which is including of the electrical losses, which is equal to the mechanical output, and that mechanical output is nothing but the gross mechanical output, and similarly gross energy absorbed by the coupling field. So what is that coupling field? The sum of field energy WES in the form of electrical and coupling field energy losses. So total losses are there. So we can represent the system with the help of this block diagram. This block diagram consists of electrical system, which is nothing but the electrical input. It is connected with the coupling field. That coupling field via some electrical connection. So it having the resistance. Let the terminal voltage is VT and the EMF induced over the armature is E. So when the current I is going to flow, then there is a I square R loss, means the resistance losses, and this resistance loss produces heat. So it produces heat due to ohmic loss. Ohmic loss. What is ohmic loss? I square R loss is the ohmic loss. Now it is get stored in the coupling field. Now heat, again there is a heat dissipation, or the heat dissipation is due to the loss. So heat due to coupling field loss, coupling field loss, and finally we get the total torque or mechanical force. Say the torque T, and you can write as a angular velocity omega r, or you can represent it into force and the velocity u. So, but as a motor, we are using torque instead of force, and velocity instead of the angular velocity, isn't it? Now, when there is a friction and windage loss, therefore, again, heat is going to produce heat due to windage and friction loss in the mechanical system. So in this way, it can be represented, this can be represented as a electromechanical energy conversion. So now thus equation 2, any change in the electrical input, you will observe the change in mechanical input and change in energy storage. So this can be represented as in the form of differential equation dW electrical is equal to dW mechanical plus dW field, stored field loss. So this is the our required equation. Now, what is the coupling field reaction? So to understand the coupling field reaction, if the output is mechanical, means it is a motor. As a motor, the coupling field must react with the electrical system in order to absorb the electrical energy from it. So if we are considering as a motor or mechanical input, mechanical conversion from electrical to mechanical, then the coupling field reactions must be such that it should absorb the energy from the electrical system. The coupling field extract energy proportional to E and I, whatever the terminal voltage or EMF induced and the current from the electrical system, and convert and deliver energy proportional to torque and velocity to the mechanical system. Thus, the reaction of coupling field on the electrical or mechanical system is essential for electromechanical energy conversion process. So therefore, it is necessary the coupling field must be there, and that coupling field is nothing but the electromagnets we are using for conversion either from electrical to mechanical and mechanical to electrical. So this is the things which is uh, must be discussed before going inside again the DC generator. Now we will consider the EMF equation of the DC generator. Now already we have discussed the construction point of view, the DC generator. So we are not again discuss the say its construction. Directly we will consider some parameter, and from this parameter we are going to decide the we are going to draw its equation. So let Let phi is the flux, per pole in Weber. What is the flux per pole? Means we are using the electromagnet. We are using electromagnet. Say this is one pole, just for understanding. There are maybe a 2 pole, maybe a 4 pole. Okay, and here there is some field winding, large number of turns, and this is the field terminal F1, F2, which is going to produce the flux because of this current in the field winding. So this flux phi produced by a one pole, by the one pole. So let the phi is the flux produced by the pole. So in Weber, in one it is produced by only say one pole. Now Z is the total number of armature conductor. Total number of armature conductors. So this is the armature. So there are number of slots. This is one slot. This is second slot. This is third slot, and so on. It having large number of slots, depend upon the design of motor. So if one slot carries one conductor, if one slot carries one conductor, then we can say that number of slots is equal to the number of conductor. But if one slot carries two conductor, instead of one, it having two conductor. So in general, we can say that the total number of conductor can be calculated as, or can be expressed as, number of slots per number of slots multiplied by number of conductors per slot. Yes. So if you want to take the total number of the number of slots is 36 and two conductor per slot. So 36 multiplied by 2. So it is 72 number of conductors over the periphery of armature. So again, I just give the name. This is the pole. This is field winding. This is armature. Okay. And this is number of conductor per slot. Whereas this is nothing but the slot. Okay. So I think it is much easier to visualize the things inside the machine. Okay. Now P is the number of generator pole. P is the simply number of poles, isn't it? It may be a 4-pole generator. It may be a 2-pole generator. If this is like this is 2-pole, whereas you can produce 4-pole, 6-pole generator, 8-pole generator, and so on, isn't it? A is the number of parallel path. A is the number of parallel path in armature, isn't it? So how the number of conductors are connected, how many number of parallel paths are there for the it is different for the lap winding and it is different for the wave winding, where n, capital N, is the armature rotation, armature rotation, that is in revolution per minute, per minute, isn't it? So it is expressed as revolution per minute. So that is nothing but the speed. It is nothing but the speed by which the armature is going to rotate with the help of external force or prime mover, isn't it? And E is the EMF induced in any parallel path in armature. Okay, so this is the, and whereas EG is the EMF generated, is the EMF generated by the generator, isn't it? Now, average EMF generated per conductor is equal to d phi by dt. What is the meaning of d phi by dt? So the rate of change of flux. Suppose one conductor is completing one rotation. So the total number of flux cut by the conductor is d phi, rate of change of, and this rate of change of is nothing but Weber, flux is Weber per second, time is in second. So this is nothing but the volt. Okay. Now flux cut by the conductor, flux cut by conductor in one revolution or one rotation, complete rotation. How much flux is going to cut? D phi. Why d phi? Because flux produced by one pole multiplied by number of pole P. So flux produced by one pole, flux number of pole is this one. So total is the Weber. It is the flux. Whereas number of revolution per second, number of revolution per second, it is equal to dt time. Sorry, it is equal to n upon 60 and per minute. So minutes, this is per second, isn't it? So therefore the time for one revolution or rotation is equal to 60 upon n second. This is the time required to complete one rotation, isn't it? Hence, as per the Faraday's law of electromagnetic induction, as per Faraday's law of electromagnetic induction, we can write as EMF generated per conductor per conductor, it is equal to d phi by dt, rate of change of flux linkage. What is d phi? It is phi p. And what is dt? Time for one revolution is equal to n up 60 upon n. So which is equal to phi p n upon 60. This is for the one conductor. Now, if you consider simplex wave winding. Wave winding, we have already discussed. This is one conductor. This is second conductor. It is connected from back. Now to produce large amount of voltage, like that, we have connected. This is the wave one, isn't it? And this winding, it is used for large voltage because the number of conductors are connected in series. So the number of parallel path for the wave connected, number of parallel path is equal to 2. Therefore, EMF generated, number of conductor in series is equal to Z upon 2. So whatever the total number of conductors divided by 2. So this is the specification or some importance for the lap winding. So EMF generated, EG, is equal to, we can write as phi Z phi Pn, sorry, this is right, phi Pn upon 60 into Z upon 2. So this is the equation for wave winding. Now this is one, this is second for lap winding. Lap winding, this is one conductor, this is second, one more conductor. So these are connected in such a way that the number of parallel path will be more. So here the number of parallel path is equal to P, means number of pole. So we can say that number of conductors per path is equal to Z upon P. So EMF generated under such condition, EG is equal to phi Pn upon 60 into Z upon P. So PP get cancelled, isn't it? So for our simplicity, we write as it is for the lap winding. So in general, we can write as EMF generated for the DC generator is phi Z N P upon 60A, where A is the parallel path. Okay. So in this case, the equation A is A equal to 2 for simplex wave winding, whereas A equal to P for lap winding, isn't it? So EMF is equal to EMF generated is equal to phi Z and P upon 60A. If it is given that it is a wave winding, put A is equal to 2. So here A is equal to 2, like that. And if it is a lap winding, A is equal to P. So this is P is over here. So this is in both. So this is the EMF equation. Now, if you comments over this EMF equation, we will observe here that for the EMF equation, just again we will write EMF equation EG is equal to phi Z N P upon 60A. This much is the volt. So here we can say Z is the total number of conductor. Once we design the machine, either it may be a motor or generator, especially generator, the number of conductors over the periphery of armature, here the periphery of armature, once we will design, we cannot change. Number of poles, once either it may be a 4-pole, it may be a 6-pole, it may be 8 poles. Once we design the machine, the number of pole again will remain same. And in the same way, the number of parallel path, either we will make the generator as a lap winding or we will make as a wave winding. So under such condition, the parameter Z, number of pole P and A are constant for a machine or generator. Okay. It is fixed during the construction only. This is during construction. Once we design or construct the motor, so what are the variable parameters are remaining? The variable parameter is flux, because it depends upon the current in the field winding and speed of the prime mover. So we can say that the flux is proportional to field current, isn't it? And speed is depend upon speed of prime mover, isn't it? So we can say that the EMF generated EG is constant Ka phi into n, where Ka is constant depends upon Z, P, and E. Okay, so these are this one. So if we vary the excitation, definitely the flux is going to increase, and when flux is going to increase, EMF also get increases. Or if we keeping the flux constant and if we vary the speed, the EMF is going to change. So it is just for discussion point of view. It is going to discuss in detail. If the speed is constant, for the particular DC generator, and if you vary the field current, the EMF generated also get varied. So let at zero field current, the flux is zero. And as the current increases in the field winding in this direction, the flux also increases and hence your EMF also get increases. So we will find such type of curve, and at particular position, the magnetic flux or magnetic material gets saturated and the EMF generated also get saturated. So it shows that the EMF generated is directly proportional to flux when speed again constant or at constant value, say 15,000 RPM or 1500 RPM and 1000 RPM and so on. So this is the EMF equation. That EMF equation is nothing but Eg is equal to phi Z and P. Z is the total number of conductor, N is the speed of the prime mover in RPM, P is the number of poles, 60, A is the number of parallel path. For the simplex wave winding, A is equal to 2, we will put 2. And for the lap winding, we will put A is equal to P. So this is the EMF equation of the DC generator. In the next lecture, we will continue with the same topic, but we will take the example of EMF generated by the DC generator and a number of poles, and say what is the flux, what would be the required flux for the particular EMF induced in the DC generator. Thank you.